get started with the afternoon session. Noah will tell us about LP norms and will dance for us, right? It's a mysterious wiggle.
Oh, no, it's not me who do the wiggle. Sorry, if necessary. Or if there's sufficient demand. I suspect there isn't. Okay, yeah, so I'm going to tell you about lattice problems in different norms. And I'm going to tell you about this very mysterious wiggly thing that I like to talk about. And okay, this is like, I'm really like talking about 3 different papers. The first one was this really big breakthrough by Eisenbrand and Venson, which actually happened, and I'll sort of tell my own personal story of learning about this result during the Simons thing 2 years ago. Although they weren't here, it just happened at the same time. And then there's sort of like a paper that I was a part of that followed up on this, and now sort of the current best results are due to Roth plus Venson. But anyway, I'll tell you this whole story. So, okay, it's a talk on lattices. I should tell you what a lattice is. Probably many of us know, but it's a discrete set of vectors in n-dimensional space. Yeah. Here's a lattice in 2 dimensions. It's very pretty. It's specified by linearly independent vectors, b1 through bn. So here's a basis for this lattice, and the lattice itself is a set of integer linear combinations of basis vectors. Of course, these are very nice algebraic objects, but we're interested in their geometry. So like maybe the most like fundamental geometric quantity that we're interested in is what we call lambda1, which is the minimal non-zero length of a non-zero lattice vector. Yeah. Of course, every lattice has 0 in it. That's not very interesting. What's interesting is the minimal length of a non-zero lattice vector. And okay, normally, like, you know, between friends or whatever, when I say the norm of a lattice vector, which happens quite a bit, I mean, yeah, I mean the L2 norm, yeah. But like, there are other norms as well, right? So there's like the LP norm, which is like the sum of the absolute values of the coordinates of x raised to the pth power, and then, okay, raised to the 1 over p. Right, so the L2 norm is just a special case of this when you plug in p equals 2. And like, okay, we all really love the L2 norm. Yeah, I hope we all agree it's our favorite norm. Like, you know, it's been good to us. But it's not exactly clear what's so special about it. I mean, it's beautiful, but like maybe we care about other norms too. And these are very nice generalizations. And in particular, there's also the L infinity norm, which is the limit as p goes to infinity. It just gives you the maximum absolute value of a coordinate. And you could be even more general. Yeah, so like Boaz kind of set me up for this, but there's like a very simple relationship between norms and symmetric convex bodies, right? So if I give you a norm, then I can define an associated symmetric convex body, which is just a unit ball of the norm, right? So in other words, the L2 norm, like literally it is the ball, the L2 ball. For the L infinity norm, the associated ball is the cube, right? But I can go the other way too, right? If you give me a convex body, I can define a norm. It should be symmetric. I can define a norm. It's just like the minimum that I have to, of the scaling that I have to scale up the body in order to get x inside of it, right? And like this is an equivalent way of defining, for example, the L2 norm, and it generalizes quite nicely. Okay, so and you know the study of lattices and convex bodies are quite deeply entwined. Like, you know, if you've heard Minkowski's convex body theorem, that's a deep relationship between the two. Okay, and I'll use the notation like lambda1 to some powery thing to mean like lambda1 in various norms. So this is lambda1, the L2 norm, the infinity norm, and some arbitrary k norm. Yeah. Okay. So I'm mostly going to be talking about the shortest vector problem. Which I'll write as SVP sub k to specify what norm I'm talking about. And the goal here is just to output a shortest non-zero lattice vector, where shortest here means in terms of whatever this norm is. So maybe this is a solution depending on your norm and this lattice. But like we care about this problem so much, and it's so important to us that like we're okay with approximation factors, right? So we often actually work with gamma SVP sub k, which is the approximate version of this problem, where the goal is to output a non-zero lattice vector whose length is within a factor gamma of the minimal length. I suppose this norm should say norm sub k. I'm probably going to drop a bunch of sub k's everywhere. It's quite annoying. Okay. So maybe this is a solution to this problem. And this is known to be hard, for example, for gamma less than n to the 1 over log n. There's some question about which norms this is known for and which it isn't, but let's not worry about it too much. And what's really beautiful, okay, there are many things that are really beautiful about this problem. One thing that's really beautiful about this problem that kind of came up during Huck's talk, I think Scott asked a question about it, is that like this problem is interesting for a really wide range of approximation factors. Yeah. So like approximation factor 2 to the n. I guess when I first show you this, it's like not clear at all what a reasonable approximation factor is. You just kind of have to get used to it. I don't know that there's any real intuition, but like approximation factor 2 to the n, that's the LL algorithm, right? So that's like one of the most important algorithms of the 20th century, I suppose, both centuries. So that's super important. Approximation factor 1, that's the exact problem. That's very important. In between, you get really interesting things too. Like you get crypto around polynomial in n. For this talk, for the most part, let's think of gamma as like a very large constant, which like I'm just going to arbitrarily write like 100 or 1,000 or whatever when I mean arbitrarily large constant. Okay, cool. And unfortunately, I have to discuss CVP just a little bit. I don't really want to have to discuss CVP, but I do. So I'm going to say it really quickly, and I'm going to use this in one place, and then we'll all not worry about it too much. So in CVP, in addition to being given as input a basis for a lattice, you're also given a target. And the goal is to find a lattice point that's close to the target. There's an approximate version of the problem, just like for SVP, where you can find an approximate closest vector to the target. Yeah, and again, it like is defined in terms of some norm. And you'll see there's one annoying place where this comes up where I have to switch from SVP to CVP, and I'm going to be very upset about it. Okay, good. What we know about this is that gamma CVP is at least as hard as SVP. This is a beautiful result by Goldreich, Machancho, Safra, and Seifert. It's a really, really strong reduction in the sense that it preserves the approximation factor, it preserves the norm, it's super efficient, it essentially preserves the lattice, not quite, but it preserves, for example, the dimension of the lattice. And like another like heuristic-y thing is that as long as the approximation factor is not tiny, things get weird as the approximation factor approaches 1 for some reason. But as long as the approximation factor is not too tiny, the algorithmic state of the two problems is pretty similar. This is a bit of a lie, but is what I want you to think for this talk. Okay, so now let me tell you a story. So let me describe the world before May 7th, 2020. So I'm sure we all remember where we were on May 7th, 2020. It was a big day. The pandemic was going on. I was in Berkeley, but locked in my apartment. And here's what the world looked like, at least like to a nerd like me, like this is my picture of the world. Right, so this is the complexity or some things that we know about the complexity of SVP in the L2 norm on May 7th, 2020. And maybe I should just specify this part hasn't changed. Yeah, so this is still what I know today. So what we knew, so like here, like this green line is like the best proven upper bound. This red line is represents lower bounds that we know under various complexity theoretic conjectures. And this blue line is what everyone thinks is true. More or less everyone who thinks about these problems has more or less the same opinion on what the right answer is. And okay, I mean, you know, there are decades of work represented by this poorly drawn graph. You know, this 2 to the n time algorithm for exact SVP is very exciting. It turns out that for large constant approximation factors, we know how to do slightly better than for the exact problem. And then for polynomial approximation factors, we know like a smooth time approximation factor trade-off. But in this like sort of trade-off regime, you still get exponential running time, right? This is the part that's relevant for crypto. And it's kind of nice that like the running time is like literally like 2 to some constant times n, as opposed to like 2 to the square root n or something scary like that. And what we think is actually true is basically the exact same thing, just the constant, the exponent goes down a little bit. And what we think, like, notice that the scale of this graph, first of all, doesn't make any sense, but second of all is ridiculous, right? In the sense that like, these are constants, and then here I'm moving between different polynomials, right? So like the scale changed tremendously here. And so like somehow the fact that this is flat here and then eventually starts going down, like actually makes a lot of sense. Because like if somehow this function is sensitive to different polynomials, it shouldn't be sensitive to different constants. Keep this in mind because it's going to be false. Okay. And we know some hardness, like we know that at least for like the exact or even the near exact problem, we don't expect to get like huge improvements. Like we're not going to find a 2 to the n over 10 million time algorithm or a 2 to the squared n time algorithm for SVP. We know that under fine grained hardness assumptions. And Huck talked a lot about how like we know barriers to polynomial time algorithms all the way up even to slightly super constant approximation factors, or good super constant approximation factors. Yes. It's a very good question. Oh yeah, so I think the question, as I understand it, is like this is presumably an asymptotic picture. It is an asymptotic picture. What about like concrete? Like if the dimensions, 347 or whatever, like what do things look like? And I think like broadly, roughly the same. In some not too small dimensions, the fastest known algorithms are not the same as the fastest asymptotic algorithms, but they're similar. Yeah.
And what do we know about the differential approximation factors?
Yeah, so this trade-off kind of keeps going. I debated just writing the trade-off. Maybe I should have, but you get like for n to the c approximation, you get a 2 to the n over c time algorithm. Did that make sense? And that works even when c is not a constant. So maybe I shouldn't have called it c. Okay, cool. Okay, and yeah, you can look up like an actual write-up of the current state of the art, and you can find this on my website, for example. But okay, like some things to notice. So this blue line, the reason we think we know the right answer is because we have heuristic algorithms that achieve this. We just don't know how to prove that they're correct, right? Is Tice in the audience? And like the reason we think that this blue line can't be brought down. So we think it can't. We think it like we know it's at least this low. The right answer is at least this low because we have heuristic algorithms that very clearly work. We just don't know how to prove it. We think it can't be brought down, or at least a lot of people think this can't be brought down because if you get a much faster algorithm for SVP, essentially for any lower approximation factor than some threshold here, then crypto gets broken in practice, right? So like in theory, the assumption that crypto is secure is like no polynomial time algorithm. But in practice, the assumption that crypto is secure is the algorithms that we know are the best algorithms up to a very small margin. Yeah. Okay. So like that lower bound, or that blue line is hopefully in the right place. Okay. So if you want to break crypto, you go below this blue line. If you want to break complexity theory, you go below the red line. Yeah. Okay. Gamma SVP infinity. The picture, maybe it looks similar, but it's actually like much less interesting. Or at least it was. This is in May 7th, 2020, right? In the sense that like there hadn't been a ton of study on algorithms for this problem. So Devesh has a very nice paper with Bianca Mudapadier, which I think is like the only paper to like really directly try to get a constant in the exponent. Before that paper, we just only had 2 to the order n time algorithms for this problem where the constant in the exponent wasn't even specified. And like this makes sense, right? Like we all love the L2 norm, like we think about it all the time. I do, at least we all do, right? Like we live in it. But the L infinity norm, people have put much less effort into. What people really like the L infinity norm for, though, is that in the L infinity norm, you can prove lower bounds. So the L infinity norm really lends itself to proving lower bounds, and Huck kind of showed why in his talk. It was a very brief moment in his talk, but he like pointed out that like this gadget that he needed was like trivial. It's just the identity matrix in the L infinity norms. This goes all the way back to Van M. de Boas in 78, something like this. Whereas it was a huge open problem to prove any hardness whatsoever in the L2 norm for 2 decades. And in fact, we know like very strong fine-grained hardness results for SVP in the infinity norm. In particular, we know under SCTH, a reasonable complexity theoretic conjecture, we know that there's no algorithm that runs in time better than 2 to the n. And that's even true for small constant approximation factors. Where there's some trade-off that's not actually explicit between like the approximation factor and the lower bound that we get. So in particular, like this really suggests, this is where I want to lie to you, that this really suggests that we're not going to see what we see in the L2 norm, right? In the L2 norm, we can do better than 2 to the n, right? A little bit better, and we think we can do way better for constant approximation factors. Here, we know that for small constant approximation factors, that's impossible unless complexity theorists are very sad. So probably just for constant approximation factors is not going to happen. Yeah.
So the difference between the two pictures, of course, only makes sense in the low gamma regime, right? Because otherwise.
Yeah. So in the high gamma regime, at some point you just hit the case where if you want an L infinity short vector, you find an L2 short vector, and you say, yeah, that's pretty short in L infinity too. That's fine, right? You lose a square root n factor, which is actually what happens right here. Yeah. So for large approximation factors, they're the same up to this sort of shift by a square root n. Okay. Cool. Yeah.
Do we know if SVP for different norms translates to some different version?
Yeah, so this is a great question. I thought a decent amount about it. The Gaussian's really nice. So like a lot of our best proofs for like anything in LP norms go through L2 norms because the Gaussian's really nice. I mean, there is LWE, right, in the in uniform error, which is kind of the infinity norm. But I don't think there's there was a paper recently, I'm forgetting the authors off the top of my head, showing that you can go from SVP in the infinity norm to LWE in uniform error, but you get worse parameters than what you would get if you went through the L2 norm along the way. Yeah, I think either the L2 norm is really nice or we understand the L2 norm really well, or relatively well. But somehow almost everything we do works way better in the L2 norm. Does that make sense?
But the Gaussian is really nice when it comes to Fractal sampling, but the Young Fractal sampling.
No, the Gauss. Okay, so the LWE reduction, Oded uses this discrete Gaussian, right? And he uses a lot of properties of the discrete Gaussian, some of them implicitly. I mean, the main thing is just that it's Fourier transform. It's its own Fourier transform, and it decays quite rapidly. Yeah, it's sort of optimal in that regard. Yeah.
Let's not dwell on this, but just a small comment. The L2 norm has vastly more symmetry than any other norms mentioned here. It makes a huge, that's what makes all the difference. The L2 norm has maximal symmetry among norms. Has
It's the largest symmetry group.
It has much more symmetry than
It has the whole orthogonal group.
It's a pervasive theme in mathematics. The virtue of the L2 norm.
Yeah. You're setting me up. I appreciate it. So, because obviously the picture is that the L2 norm is the easiest norm to work with by far, right? And yeah, I guess as Greg's saying, there are reasons for this. I'm saying maybe it's a cultural phenomenon, but no, there are in fact reasons for this. But okay, so 2 years ago, I gave a talk not dissimilar to this one, in which I listed a bunch of open problems, and I gave an easy one. So I ranked them according to sort of ski notation, even though I don't ski. And I gave an easy one, which was just give better algorithms in the LP norm. And what I meant by that wasn't I wasn't asking for anything fancy. I wasn't asking for anything useful. I wanted lower bounds for my lower bounds. Yeah, I've proven lower bounds on SVP in the infinity norm. So I would really like someone to show that my lower bound is tight. And that means someone has to find an algorithm. So that's all I was hoping for. So I was hoping that someone would say, okay, there's a 2 to the n time algorithm for SVP in some LP norm, p not an even integer or whatever, and then my lower bound's tight, and then I can be very proud and I can stop thinking about lower bounds. Yeah. It worked. May 7th, 2020 came around, and I got this email from More Expensive. The title was Faster Algorithms for SVP and CVP in LP Norms, question at Simon. So I think he'd watched the videos of the talks, which by the way are a tremendous resource. So he was emailing me to answer my question, and I was like, oh great, I hope it's 2 to the n, okay, maybe if it's 2 to the 2n, that's still pretty cool, that's just a factor 2 of the exponent, among friends, not a big deal, but this is what he sent me. So that's less than 1. right? The constant in the exponent is less than 1.
But it's only for even p.
Nope, it's for all p. So this is a result that is not well enough known. I should have said this at the very beginning of my talk. The main reason I'm giving this talk is because I think people aren't aware of these results, and I just want to evangelize for them. Mostly not my own results. I suspect there are many people in the audience who would be consumers of these results if they knew about their existence. So what Moritz sent me was a paper saying he had an algorithm for 2 to the 0.8 n 2 to the 0.8 n time for CVP in LP norms, which in particular implies it for SVP and LP norms. Of course, there's this word approximate here. But like, my first thought was like, oh, okay, there's a bug, or oh, okay, there's a bug in my hardness results. Oh no. And this constant, like, if you hang out enough in this area, this constant by heart. This is the best known running time for SVP and the L2 norm for large constant approximation factors. So the specific constant's not so important. It's less than 1, but like it has meaning just in the sense that it comes from L2. So basically what they were saying is LP is just as easy as L2. Yeah. And okay, the reason this doesn't contradict my lower bound is because it's for large constant approximation factors, like, unspecifiedly large constant approximation factors, maybe 1,000. Whereas my lower bounds only apply to very small constant approximation factors.
Does that unspecified constant depend on p?
Right now it does. Later in the talk it won't. I'm going to improve the result. So yeah. Actually, a lot of the stuff that I'm saying is kind of misleading until the most recent result. Okay. So here's the world after May 7th, 2020. This is just SVP infinity now. And what happens is for small constant approximation factors, we still know relatively little. Like even for very small, we don't even know an explicit constant in the exponent. Nobody sort of bothered to work it out essentially. But once you get to a large enough constant, suddenly this just becomes SVP in the L2 norm. And it just behaves exactly like SVP in the L2 norm. And in particular, it goes down to this specific 2 to the 0.8 n. And actually, as I'll show you later, that continues for all approximation factors. So we now essentially know that once you hit a large enough constant, SVP in the L infinity norm becomes more or less the same as SVP in the L2 norm, in the sense that our fastest algorithms for both run in the same time.
So is that a formal statement that there is a runtime preserving and nearly approximation factor preserving reduction from
These are spoilers. I mean, okay. But even before Vinod's question, right? Okay, so that means that the blue line here has to match the blue line. So remember, the blue line is our best guess as what's true. It has to match our best guess as to what's true for L2, right? Like it's as low as our best guess for L2, at least for large enough constants, because you can plug in your favorite L2 algorithm and you'll get that immediately. And it can't be lower because again, if it's lower than that, you break crypto. So like we absolutely really hope that this is the right answer. But then what happens here? This is the thing that confuses me. And I'm now in danger of pointing at a slide and saying I'm confused about where this line goes for 10 minutes, but I think I might do that. We'll see how it goes. Like, so what the hell happens here, right? There, and remember, like, if this ends up going below the red line, you break SETH. That's very sad for complexity theorists. And like, not only do you break SETH, you break it by an algorithm for SVP in the L infinity norm, which like doesn't seem super plausible. You go here, you make even more people sad. You break a bunch of crypto.
So again, the best that's known below this like threshold gamma is n to the n. Is that right?
No, there's 2 to the order n with unspecified constant.
Depends on which depend on p. Depend on p.
Yeah.
Like for infinity, what's the?
No, 2 to the order n. 2 to the order n. I'm only talking about infinity because it's a cleaner picture there. So here are the only possible resolutions, I think. I'm pretty sure I just used the law of excluded middle. So option one is that the line wiggles. And I don't know if that just seems totally reasonable and plausible to you. To me, it seems absolutely absurd. And I want to remind you of the ridiculous scale that this is on, right? Right. So these are constant approximation factors. These are different polynomials like n and squared and cubed. And what this is saying is that for constants, you get 2 to the constant times n, where there's a trade-off in the constant in the exponent as the approximation factor changes. Then the thing levels off at some constant for some reason. And then later for polynomials, it starts getting the same trade-off again. Like, what's an example of a thing that does that, right? Okay, if you don't think that's absurd, then I'm talking nonsense, and maybe it's not absurd. But to me, that's completely absurd.
There's something like that for function field set, number field set trade-offs. It's weirdly wiggly, but I mean, nobody I think would say, "Oh, that's clearly the best algorithm."
Yeah. I mean, this has been like we've always had something that looks like this for our best known algorithms. We've never thought it was the right answer.
Yep.
This is saying that either this is the right answer, it really is a wiggle, or SETH is false, or lattice-based crypto is way less secure than we think it is. I think those are the only 3 options. And so probably the most likely is the weird wiggly line.
So can you explain again what the weird wiggly line is?
Yeah, so it means that there's some as I go from, I don't know, 10 approximate SVP infinity to 1,000,000 approximate SVP infinity. Yeah, the running time goes from, I don't know, 2 to the 2n to 2 to the n. Yeah. And then it levels off it has to level off at exactly 3/2 to the n over 2, but it levels off at some explicit constant. And then for very large constants, it's just flat. And then you start seeing the same kind of trade-off again for polynomials. Then you start seeing at order n, it's like 2 to the n over 10. At order n squared, it's 2 to the n over 20. Yeah. So I don't know. This is what I call the strangely wiggly line. I think I'll write a paper on it. It'll be more explicit at some point.
No,
Okay.
what's going on the algorithmic side? Like you said, this is the ground truth for best known algorithm. So are you just using like a completely different algorithm later? Like,
What do you mean?
like on the algorithmic side, what is it that makes the problem like starts becoming easier again later while there's no improvements like at the large constant?
Yeah, so basis reduction, right? So we know a trade-off for polynomial approximation factors. And if for large constants, we kept getting improvement, it didn't level off somewhere, then that would break crypto.
And just to clarify, you're saying that smoothing one of the wiggles would break Seth and smoothing the other wiggle would break crypto?
Yeah. I'm not sure if it's 2 wiggles or 1, but yeah.
All right, smoothing it out in one place.
Yeah.
Okay. And I mean, is it possible that we're just looking at it with a funny parameterization of gamma, and if we just changed how we were plotting the range of gammas, that it wouldn't look as wiggly?
I think it's the right way to parameter. You mean in terms of parameterizing in terms of the rank or the dimension or whatever?
Well, I don't know. I mean, it's like you're going from what are all the gammas that are being talked about numbers, or are some of them like functions?
No, some of them are functions.
Some of them are functions of n. So
yeah,
it's very hard to plot like numbers and functions of n.
No, but I think that makes it more surprising, not less surprising, actually, right? Because somehow for constant approximation factors, the kind of trade-off that you get is it's still exponential, just the constant changes. And then it happens again for polynomial approximation factors, right? These scales are tremendously different. Yeah. But this is just a feeling I have. Maybe I'm crazy. Okay. Okay. So let me actually tell you how this algorithm works. It's so I'm going to show you an algorithm that solves constant factor approximate L infinity, SVP and the L infinity norm in running time that's the same as what you get for the L2 norm. And it's I mean, it is an algorithm, but like it's not really an algorithm. It's three observations. So observation numero uno is that the fastest algorithm for SVP in the L2 norm with large constants is 2 to the 0.8 n. I think I've said this sentence a million times in my life. Observation number two is that this algorithm doesn't just find an approximate shortest vector. It finds a gazillion of them. In fact, it finds exponentially many. And this, like, if you've done anything with lattice algorithms before, you know that this is a very common feature. Yeah, I mean, this is a sieving algorithm. And the two kinds of algorithms that we have are basically sieving algorithms and enumeration algorithms, and they both very much have this feature. I'm being slightly hand wavy here because I want to pretend that what this means is you get exponentially many, is that you can use this algorithm to get exponentially many distinct lattice vectors at any radius above, say, a constant times L2 lambda 1. That's not necessarily true because there might not even exist such vectors. But that turns out to be the easy case in all these algorithms. So I'm going to sweep that under the rug for the most part. I'm going to pretend I get a bunch of distinct vectors. Okay. Observation number three, which is like the only thing that's new, is that if you have many L2 short vectors, you can use that to get an order 1 approximate L infinity shortest vector. And let me tell you how that happens. So let me scale things so that lambda 1 in the infinity norm is 1, which means lambda 1 in the L2 norm is most square root n, right? Like cubes and balls, yeah? Okay. Okay, so here's the claim, the geometric claim. It's if you've got a bunch of vectors in n-dimensional space whose L2 norm is at most square root n, and there are at least 2 to the n over 10 of them, say. These constants might be wrong. They're probably okay, though. Then there has to exist a pair of them that are close in the infinity norm. I'm going to sort of show you the idea behind the proof of this. I'm not going to prove it to you. But let's just immediately notice that this implies this up to this little annoyance about vectors being distinct, right? Like in particular, if I can get many L2 short vectors, then I can just check all pairs and output the pair whose L infinity difference is minimized. And just like even in the worst case, like no matter what, there has to be a pair whose L infinity distance is at most 1,000. There's some issue that you might get 0. There's always an issue you come up with, your like a crazy fancy SVP algorithm, and then oops, it outputs 0. This could be a problem. It's not an actual issue here, but I'm gonna ignore it.
Is this just a volume argument?
Well, I don't think a volume argument would be tight enough. You get like a 1 plus epsilon to the. I don't think you can quite prove it directly with the volume argument, but I'm not totally sure. But what I do is what they do is similar. So the whole point is just you can cover if you take the root n ball. So in other words, the ball L2 ball scaled up by a factor root n, which is big enough so that it contains the cube. The point is you can cover this by 2 to the n over 10 cubes with side length 1,000, or if you like, sort of L infinity radius 500. Yeah, and okay, like I'm not going to show you a proof of this. Actually, by far the best proof, of course, uses the discrete Gaussian over lattices. This is really a question about counting the number of short vectors in Zn. Think about it, sure. Okay. And just a little technical detail for those who are like super into this stuff. The specific property of the L infinity ball that I'm using here is that root n times B2 contains B infinity, but it can be covered by many copies. So like somehow being covered by many copies isn't super surprising. This is like an M ellipsoidy thing, and I'm going to say more about that later. The fact that it's literally contained is the magic here, and this is why this doesn't immediately translate to all norms. And okay, Eisenbrand and Vincent showed a similar algorithm that doesn't just solve SVP, it solves CVP, and it works in any LP norm. Actually, like they have one algorithm for p greater than 2 and one algorithm for p less than 2, which is a common thing that happens. So this is crazy, but like, let's complain, yeah. So there are things to complain about. The biggest thing to complain about here is that it's an algorithm, not a reduction, right? And why is it an algorithm, not a reduction? It's an algorithm and not a reduction because like I had this list of 3 observations, right? So like I need an algorithm with certain specific properties. I suppose it's this one. And like, you know, when you start dealing with the actual issues here, what you actually need is a rather subtle specific property. I need an algorithm with specific properties in order to make this work, right? And that's like a downer because it means like, you know, if someone finds a faster algorithm in the L2 norm tomorrow, then it's not clear what that will say about the infinity norm. It also only works at constant approximation factors. We'd like to say, I mean, now that we have this result, like now we'd like to just go crazy and say like, okay, for all approximation factors, the two problems are more or less equivalent. But this only works for constant approximation factors because it's at constant approximation factors where our algorithms have this property. And it only works for LP balls. And actually, the fact that it only works for LP balls is more annoying than you might think, because I've been hiding this entire time the distinction between the rank of a lattice and the dimension of a lattice. And you can do this in the L2 norm, because in the L2 norm, if you have some lattice that's like low rank, but embedded in some gigantic dimension, you can just pretend that you're working inside the span of the lattice, because the intersection of the ball with that subspace is going to be a ball. Yeah, but for LP norms, that completely collapses. In fact, intersections with the cube are essentially arbitrary convex bodies, more or less. Okay.
So like what's the smallest value of 500?
Smallest value of
I don't know, like, is it, did they work it out? Like,
they didn't, we did, but I don't know the answer off the top of my head. Yeah, okay, on the next slide, I have slightly more detail, but not enough detail for you to actually reconstruct that. Okay, so now let me briefly tell you about work that I was actually a part of. This is joint work with Devesh, who's over there, Rajendra, who's somewhere there, Yanlin Chen, Zhang Li, and some clown. And you'll notice we got dimension preserving reductions between SVP and CVP. And our main observation, which I'm just not going to tell you about at all, is that any approximate SVP algorithm or CVP algorithm can be converted into an algorithm that samples randomly for more or less the set of solutions to the problem that it's solving. There are a lot of details, like what we actually get is subtle, particularly because there might not be that many solutions in the first place. But this works, and the key word is sparsification, if you know what that means.
so like you run this SVP algorithm once per point that you're getting, or somehow you
many times
you generate many.
many times, yeah. Right, so like, yeah, sparsify, call it, maybe fail, sparsify, call it, maybe fail, over and over and over again, but 2 to the epsilon n times. Yeah, so what we get is 2 to the epsilon n time reductions that preserve the rank and the dimension between LP and LQ norms. We even drew a pretty picture which has some details in it, in case you're curious. But of course you can look at the paper, which even has explicit constants for what it's worth. So this is cool because like now we have a reduction, but it's still unsatisfying. There's like some annoyance that like for SVP, Q has to be larger than P. For CVP, P has to be smaller than Q. It's very upsetting. And this is because of this thing about the cube I mentioned earlier, or whatever. But we did in fact show that these things can be made into reductions. And again, like the whole point is that you can take any algorithm and make it an algorithm with the property that Eisenbrand and Benson needed. And this now works for arbitrary approximation factors, right? So you put in any approximation factor here, you get constant times that approximation factor there. You run in 2 to the epsilon n time. If you're in the regime where this is an exponential time algorithm, who cares about a little 2 to the epsilon n? Yeah. Okay.
Great.
Mm-hmm.
So I wonder, you sort of generalize this enough. So the LP ball and the LQ ball, with the inequality that you got, they have a certain relationship. like, for instance, that, there'll be bounds on a positive distance, and there'll be a volume comparisons and things like that. So could you define a favorable pair of convex bodies that aren't necessarily as special as that LP norms, where you then get the same term?
So I'm about to get for any norm.
Oh,
Yeah.
well,
Right. So the downside of this is that, again, it only works for LP norms, and that's a downside just if you like other norms, but it's also a downside if you like lower rank lattices. Because once you start taking intersections of subspaces with LP norms, you just get arbitrary norms anyway. So you might as well talk about arbitrary norms. So this was the second surprise from Moritz Svensson and Thomas Rothfuss, who showed, well, they called it an approximate CVP algorithm for in time 2 to the 0.8. This is the constant that we're all memorizing now in any norm. Yeah. So they got rid of the this annoyance. Okay. So let me tell you, they actually have two theorems.
So what in the previous result prevented you from going to arbitrary norms? This covering, this sort of the covering. Line.
Yeah. So we want, okay. I always get confused about this when I think about it, but like you want the ball to contain the cube, like literally just rigidly contain the cube. There can't be a little corner sticking out, and you still want to be able to cover the ball with
this
cube.
doesn't, if I understand correctly, this doesn't quite obviate what you were doing before, because you get 2 to the epsilon n.
So we got reductions that run into the epsilon n time. One implication of the reductions that run into the epsilon n time is that like the up to the little epsilon, which gets swallowed up by this exponential, you get an algorithm like this. What they actually get is a 2 to the epsilon n time reduction, as I'll show you right here. So what they actually get is a 2 to the epsilon n time dimension preserving reduction from approximate SVP in K norm to CVP in the L2 norm, right? Where the constant, where the approximation factor just goes up by some constant, which depends on epsilon in a not too hideous way.
Now it became CVP.
But now it became CVP. Yeah. So this is like, as I'll say when I mention open questions, this is the one remaining annoyance, right? We need a CVP oracle. And right now that's okay, because right now our best SCP algorithms like kind of also solve CVP. But it's entirely plausible that tomorrow that won't be true. In fact, that would be a very nice tomorrow. So this is very sad. They also, just to give a complete list of their results, for constant factor approximate CVP, they just give an algorithm that runs 2 to the 0.802 n time for any k, but this it's not a reduction. And also I'm trying to ignore the distinction between CVP and SVP as much as I can, so I'm not going to say much about this. Okay, so but this is, if that were an S, this would be the holy grail of like this line of research, right? Okay. Cool. So let me like briefly run through a high level sketch of slides look much better on the screen. Maybe you guys already realized that. Okay. So step 1, or really step 0 in their algorithm, is to apply a linear transformation to K, so that looks roughly like an L2 ball. And okay, for annoying technical reasons, it's going to be convenient for me to have it be an L2 ball divided by 20. So the L2 ball of radius 1/20. Now, if you do any convex geometry, you know that this is always step 0, right? Like, in fact, there's like a gigantic body of literature asking the question, when can I transform a convex body under linear transformation such that it looks like an L2 ball in some specific, by some specific definition of looks like an L2 ball. So here I'm going to show you the algorithm first, and then we're going to back out what properties of the L2 ball we need our body to have. Okay. So now like our body, you know, started out this hideous octagon thingy, and now it's a less hideous octagon. I think it's an octagon, yeah. Cool. So like now here's the setup. So like let's assume things are scaled so that the shortest vector in the K norm has norm 1, which means it lies right on the edge of this body. Yeah. So step 1 of the algorithm is to sample a target T from a rather funny set, actually, the set K plus the L2 ball. So this is like a Minkowski sum. So this was my artist's impression of what the K plus an L2 ball. Honestly, I feel like I did a pretty good job. But that's the Minkowski sum, right? So like in other words, it has it goes to distance exactly 1 from every point on the edge of this thing. So we're going to sample a uniformly random point there, and we're going to hope that we get really, really lucky, right? We're going to hope that it just happens that the distance between the target that I sampled randomly and the shortest vector v is less than 1. This is L2 distance. And like the whole reason I'm doing this, like in the L infinity case that I showed you earlier, what I needed was a ball that contained the shortest vector, the shortest L infinity vector. Yeah. That's why I needed the ball to contain the cube. Here I found a ball that contains the shortest K vector, shortest vector in the K norm. The only issue is that's no longer a centered ball. Yeah, it fundamentally cannot be a centered ball if I want the scalings to be reasonable. Okay, so that's step 1. So now I have this ball that contains the shortest vector. Now I'm just going to kind of do the same thing again. So what I'm going to do is I'm going to use a CVP oracle in the L2 norm to find many random samples from lattice points that live in a larger ball, right? So this ball contains a lattice vector, which means if I call an approximate CVP oracle on this target, I'll get a bunch of lattice vectors in this larger ball, where like the ratio of these two radii is my approximation factor gamma. Yeah, I lost people. Good. So I'm going to get many random samples, so y1, y74, yn. And then finally, I'm just going to take this bunch of samples, and I'm going to take all pairwise differences, measure their K norm, and see which one's smallest. I mentioned briefly, there's a corner case when you get the same vector over and over and over again. If you get the same vector over and over and over again, it's V output that. But okay, that's not the interesting case. Cool. And the reason that this works is exactly the same argument I went through before. What you want is you just want to cover this ball by scalings of K. Yeah, and if you can cover this ball by say 2 to the epsilon n scalings of K, then you'll get 2 points that have to be in the same scale. Yeah, just by the pigeonhole principle. Okay, so this is our algorithm. And the question is like, what do we need? What properties do I need of my ball of K for this to work? Yeah, and so for step 1, remember I sampled vector T from this like sum set thingamajig, and I hoped that it happened to land close to my shortest vector. Yeah. So what do I need for that? I need the ratio of the volume of this sum to the volume of the ball itself to not be too large, right? I want to land inside this ball. I'm sampling uniformly from this whole thing, so I want the ratio to not be too large. So I want it to be like 2 to the epsilon n, so 2 to the n over 10. Yeah. Thing 2, or thing 3 really, is that I need, as I said, the ball to be covered by 2 to the n over 10 copies of the K ball scaled up appropriately, scaled up by some large constant. Yeah, because then I only need 2 to the n over 10 samples for this pigeonhole argument to kick in and for me to get a difference that's small. Okay, so those are the 2 properties that I need. I'm not going to say much more about it, except I'm just going to point out that if K were actually the L2 ball with radius 1 over 20, this would in fact work. Yeah, in fact, it would this would be overkill. I could cover it by 1 copy or whatever. So these 2 properties together really do sort of suggest that you look something like an L2 ball, which is what we want. And of course, Rothfuss and Benson show how to not only that such a linear transformation always exists for any convex body, but that you can find it efficiently, or I think actually in quasi-polynomial time, but okay.
Sort of like the John's theorem, right?
Yeah. Yeah, so John's theorem is one of a long sequence of theorems that say in various different ways that convex bodies look like balls.
This is this is way stronger. I mean,
Yes.
John's theorem
Yes.
is like some sort of baby lesson. and
Yeah.
This is a much stronger,
Yes.
good position theorem. than
Yes.
In what sense, that you're getting balls rather than ellipsoids, is that?
No.
No.
The ellipsoid is just the linear transformation.
Well, John's theorem says that the best ellipsoid for a convex body is the largest one inside. Simple argument, you need the largest one, and then you get bounds of how far the convex body can stick out. So this thing with covering numbers, there's an ellipsoid, so that they're there's an exponential covering conversion.
For John's theorem, if you apply John's theorem directly here, you get n to the n. N to the n over 2.
Right.
That
Because of the square root
ellipsoid-
and.
Is the square root.
That ellipsoid even exists
Yeah.
was not known at all in the argument, even if there's an algorithm argument, it's much more sophisticated than what
Yeah.
John is doing.
Yeah. But
Although
this is
John's
very
theorem
simple.
Great. It's great for being easy. This isn't great that way. It's great for being true.
John's theorem is also great for being true.
That's true too.
Yeah. I mean, what this is very similar to, but annoyingly not exactly, is the M ellipsoid. Or I called it M position because I'm thinking of transforming the body instead of transforming the ball. M stands for Millman. All these things have bad names because they just use initials. So, anyway, yeah, this is very similar to M position. Actually, it's really similar to what was used in the Douche-Vempala, where they used some variant of M ellipsoids as well. Okay. Good, right. So it's not obvious that these things exist. It's also not obvious that you can find them efficiently, but both things are true. Okay. Might actually finish slightly earlier, which is kind of fun. Then maybe I will do a dance. Okay.
You said it, not I.
Yeah, no, I said it. Okay, so in summary, we now know that the fastest algorithm for CVP and SVP in any norm for large constant approximation factors is this 2 to the 0.8 n time algorithm. And like, go back and check your papers. Like I probably saved you a square root and an approximation factor somewhere. Like this should be better known. More generally, we can reduce SVP in any K norm to CVP in the 2 norm, just costing us a constant in the approximation factor. The penalty that we pay is you have to run in 2 to the epsilon n time. And I'm going to go out on a limb and make a completely ridiculous statement, which is that basically lattice problems in any norm are equivalent up to a constant in the approximation factor. I think that's what you should get out of this talk. Admittedly, it's a warm, fuzzy feeling. It's not a concrete statement. But I just want to point out this is exactly the opposite of what I thought 2.5 years ago, which is maybe a good reason not to listen to me now. But this really changed my perspective on SVP in different norms, which is a thing I think about quite a lot. Okay, let me finish just with some fun open questions. So like kind of the obvious open question is to get a reduction from any norm that goes from SVP to SVP. Yeah. By the way, there's nothing super special about the L2 norm here. Like probably all these techniques go from any norm to any other norm, but like L2 is nice. So we've been dealing with L2. Maybe we're making the same mistake we always make, focusing too much on L2. Right. So currently we have a reduction that goes to either gamma CVP in the L2 norm, or you can reduce from gamma SVP in an LP norm for p greater than or equal to 2, which is like okay. So that's problem number 1. Problem number 2 is figure out the best running time for SVP in the infinity norm for small constant approximation factors. And in particular, what's the shape of this wiggle? Yeah, seems to wiggle. How does it wiggle? And if it doesn't wiggle, then break SETH. Okay. More generally, what's going on with SVP in arbitrary norms? Like I feel like now that we really have a very nice understanding of large constant approximation factors, let's just finish, let's just figure everything out. Let's just see what's going on for small constants as well. And then this is an extremely ambitious open problem, black diamond, maybe it should be double black diamond. So the norm doesn't matter, yeah? Our best algorithms are in the L2 norm. But who says, yeah? So if the norm doesn't matter, pick your favorite norm, solve SVP in that norm, and back out the L2 norm, right? I don't think this has been tried before. I don't think people have been thinking, like, what's the silliest norm I can come up with to solve SVP in? In particular, can you make a norm, since we only have one idea and it's called sieving, okay, two ideas, sieving and enumeration. Like, why don't we just pick a norm in which sieving works really beautifully? And actually, this is quite a concrete question in the sense that there are kind of two things that control the running time of a sieving algorithm. One is this like sort of purely geometric thing, which is more or less the Kissing number. And the other is how well we can do locality sensitive hashing. So I think you could actually convert this into a purely geometric question if you stare at it for long enough. And then there's a question, can you do better than L2? This, you know, I think this is of the many implausible directions that we have for breaking lattice crypto, this is maybe one of the most plausible. Okay, thanks.
Question, just to make sure I understand what you're saying at the high level, right? There seems to be two parts to it, right? One is you can take any SVP2 algorithm and make it produce any random solution instead of just one, right? Now that uses some properties of SVPs, how short of sectors lie and so on.
Yes, exactly. Yeah.
So in some sense that uses two norms, crucially at the moment.
No. We can sparsify in any norm. No.
You can do it for any norm.
Yeah.
And the second part is your pigeonhole argument. It says once I produce exponentially many L2 short vectors, some distance is good in the algorithm.
Yeah.
And that's general, right?
Yeah, I mean, but it's what's the word I want? It's like it's delicate to make it work exactly, right? So like this is why we currently need CVP. Yeah, it like morally it's just like an M ellipsoidy thing. But getting precisely what you need, yeah, we're still.
That's why the two to the n over a constant. That's something. Otherwise, you can do John ellipsoid all.
Yeah. Exactly. Yeah, I care about the constant, right? Which is rare. Yeah. Well, one thing to correct, it's not my idea.
No.
Okay, cool. It's Eisenbrand and Vensium. Yeah. Cool.
So does this imply anything about hardness for SVP in the two norm, right? Going the other direction, right? Show hardness in some norm, and then your reduction.
Yeah, it would if we didn't already know it. Like, I mean, like we have like, you know, 2 to the epsilon or even explicit constants like 2 to the n over 100 hardness for SVP and some LP norm or whatever.
I'm talking about exact hardness for sort of the. Oh, sorry. What do you mean? Oh, I don't mean ETH hardness. I really mean like.
Oh, but it runs into 2 to the epsilon n time. So it needs to be in like the ETH regime, right? Like,
yeah.
Okay. Yeah. Although I should say, like, I've been focusing, and actually, Rothfuss and Benson entirely focus on the regime when epsilon is constant. It doesn't have to be. You do get some smooth trade-off. But I still don't think it's gonna buy you something as strong as hardness.
You're saying that would require you to show hardness in K norms to within very large factors, and then that's
Exactly. Yeah. I don't think there's a regime where it works. So admittedly, I haven't written it down. Maybe it just does. That would be pretty cool. Yeah.
All right. Let's thank Noah again. Back at 3:30.